Alright, so today we will begin the long lecture on geodesy, projections, and coordinate systems. As we've seen, geographic information systems are different from other information systems because they contain spatial data. We know that these spatial data include coordinates that define location, shape, and extent of objects or boundaries we are seeking to represent. Historically, we have represented location with a set of coordinates, an x and y, even though we know the Earth is round. When we are focusing on smaller areas, this is not much of an issue. But if we were to zoom out and observe a large area, like Texas, we would need to make sure we are accurately representing space on the surface of the Earth. Lucky for us, some geospatial math geniuses developed the field of geodesy, the science of measuring the shape of the Earth. This is what we're talking about today. We're laying the base set of knowledge for you all. We need this before we can move on to more advanced topics. We need to be able to describe the data based on locations like coordinates. But we also need to understand how we get these. Globes are wonderful representations of the world. We can see on this globe the curve of the Earth, some generalized map features like elevation, as well as accurately shaped and sized countries. So what's this downside to using globes? Well, I'm obviously not going to carry the globe around with me everywhere I go. It doesn't quite fit in my pocket like a cell phone. So we need to take this globe and we need to visualize it on a flat piece of paper. I can roll up or fold a piece of paper and easily bring it with me anywhere I need. The issue lies in the faulty design of the planet, really. I mean, why wasn't the planet just started out flat, or at least a cube? That would make mapping a lot easier. Alas, the world is not flat. It's, in a general sense, round. So when we try and display the Earth on flat paper, we're going to have to deal with the skewed or distorted features. So before we get to specifying a coordinate system to use, we must first define the shape and the size of the Earth. We know that the Earth is a sphere. Babylonians believed the Earth was a flat disk floating on an endless ocean that you could quite literally sail off the edge of. The Greeks were the first to define that the Earth was a sphere, and quite unfortunately, there were still, however, though, and quite unfortunately, there are still some organizations and activist groups that believe the Earth is flat. Those people have many varying theories, most of which are absolutely ridiculous, but at least their existence resulted in a BOB Dr. Neil deGrasse Tyson rap battle on the subject. So, ignoring the non-believers, let's take a look at some early attempts to measure how far around the Earth was. Aristophanes calculated the circumference of the Earth without leaving Egypt. Aristophanes knew that at local noon on the summer solstice in the ancient Egyptian city of Suanet, located on the Tropic of Cancer, the sun would appear at the zenith, directly overhead. He knew this because he had been told that the shadow of someone looking down a deep well in Sian would block the reflection of the sun at noon off the water at the bottom of the well. Using a gnomon, he measured the sun's angle of elevation at noon on the solstice in Alexandria and found it to be 1/50th of a circle, south of the zenith. He may have used a compass to measure the angle of the shadow cast by the sun. Assuming that the Earth was a spherical 360 degrees and that Alexandria was due north of Syene, he concluded that the meridian arc distance from Alexandria to Syene must therefore be 1/50th of a circle's circumference, or 7 degrees and 12 minutes of a 360-degree circle. Uh, Poseidonus calculated the Earth's circumference by reference to the positions of the star Canopus. As explained by Clemedes, Poseidonus observed Canopus on but never above the horizon at Rhodes, while at Alexandria he saw it ascend as far as 7.5 degrees above the horizon, which is the meridian arc between the latitude of the two locals is actually 5 degrees and 14 minutes. Since he thought Rhodes was 5,000 stadia due north of Alexandria, and the difference in the star's elevation indicated the difference between the two locals was 1/48th of the circle. So we multiplied 5,000 by 48 to arrive at a figure of 240,000 stadia for the circumference of the Earth. Now, he was not off by that much. It actually was just about 1,400 kilometers. So, how can the Earth measure smaller around the poles? Seeing here that it's 40,075.16 kilometers around the equator and 40,008 kilometers around the poles. Well, mathematically, the Earth is more like an ellipsoid with a major and a minor axis. So putting that in picture, you can see it here. The dashed line would represent a perfect circle, while the pink circle represents a more accurate kind of generalized shape of the Earth. Thanks to geodal bulge, which is caused by the rotation of the Earth, it actually tends to flatten out a bit along the poles and stick out more at the equator. So an ellipsoid has two axes to be aware of. But don't worry about the math specifically for this course. Just know that the Earth has two axes, a semi-major axis around the equator and a semi-minor axis around the poles. This difference in a polar equatorial radii can also be described by the flattening factor, as shown in this figure, excuse me. So, we know that the Earth isn't a perfect ellipsoid. Just think mountains and canyons. We like using these to model the Earth because the math is easier, and I'm sure you can all appreciate that. The ellipsoid only uses two axes, opposed to the infinite that exist in reality. But we don't just use one ellipsoid for the entire Earth. Different areas use different ones based on need and geographic fit. What models the area of study the best? The ellipsoid was not widely used before because land surveys were not conducted at a global scale until recently. In fact, they weren't even possible. Oceans and large seas were impossible to accurately measure across, and air balloons weren't an effective approach to high precision aerial surveying. Then, once we had enough of the terrestrial Earth measured locally, our maps didn't quite fit together. Translating surveys between different regions became a problem, and geodesy arose from these issues as the solution. So, if the Earth is not a perfect sphere, or a perfect ellipsoid, what is it? Well, how about I tell you what? This is the latest and greatest in geodesy. This is a gravitational model of constant gravitational pull. Gravity is a function of mass in some areas is more dense or greater in certain parts of the Earth than others. But gravity is showing where the Earth is more and less dense, not mountains or valleys. False coloring here on this model shows us that where the surface is dark blue, the Earth is more dense, and red is less dense. This does not change the fact that gravity is constant. So what is this? Well, like it says right there, it's a geoid. So, what is a geoid? Well, geoids were born out of measurement. Geoids are the closest approximation to the Earth's shape based on gravity measurements that help us define global mean sea level. Like we said before, it's a 3D surface of constant gravitational pull. The geoid is also a measured and interpolated surface, but it is not a mathematical surface like a sphere or ellipsoid. Interpolation means guessing inward's best guess. Think back to our raster of the Corpus Christi. When we zoomed in closely, we saw each cell contained one color, even though there was more detail in that area in reality. We interpolated the area as the most common color because we couldn't show every bit of reality. The interpolated surface model of a geoid is doing the same thing. Since we need measurements everywhere, but we can't get them everywhere, our geoid model can provide an accurate estimation of geoidal height for any point on the globe. So, there are a lot of different methods for measuring the geoid. Uh, Historically, plumb bobs are the oldest way and most basic way that we can do this. We could use gravimeters to measure gravity at specific locations across the Earth. We could monitor variations in orbit of satellites as they move closer and further away from the surface of the Earth based on gravitational pull. And then, of course, we have satellite-based measurements. And that's where we enter the GRACE twin satellites, which currently are in the process of creating a large gravitational model of the entire Earth. Thanks, NASA. So, from our GRACE satellites, here we could see geodal height variations above and below an ellipsoid. You can see that the dark blue is where it's actually a higher bit of gravity because we are far below the ellipsoid. And red is where the gravity has less effect as it's sticking out past the ellipsoid. So, the accuracy of GPS height measurements depends on several factors, but the most crucial one is the imperfection of the Earth's shape. Height can be measured in two ways. GPS uses height, or lowercase h in this figure, above the reference ellipsoid that approximates the Earth's surface. The traditional orthometric height, represented as the capital H, is the height above an imaginary surface called the geoid, which is determined by the Earth's gravity and approximated by mean sea level. The signed difference between the two heights, the difference between the ellipsoid and geoid, is the geoid height, or capital N in this figure. The figure here shows the relationship between the different models and explains the reasons why the two hardly ever match spatially. So again, here's another approach of looking at it. Here we can see our orthometric height is capital H, standing above our geoid, going to the actual surface or the point at which we are taking our measurement. We have our ellipsoidal height, which is our lowercase h, which is the measurement from our ellipsoid to our GPS unit, and then our geoid height, which is represented with a capital N, showing the distance from our ellipsoid to our geoid model. So, geoidal variation is the main cause for different ellipsoids being employed in different parts of the world. Here, you can see with the dashed line represents a ellipsoid B, and the solid black line represents an ellipsoid A, while the transparent gray line represents our geoid. We can see at different points in the Earth, we have different ellipsoids fitting better. This is important when we look at something like this. You can see here how the red ellipsoid representing North America, it fits really closely to the geoid. And then the blue ellipsoid fits the geoid well in Europe. So if we were taking measurements in North America, we wouldn't want to use an ellipsoid best fit for Europe, and vice versa. Alright, so now let's talk a little bit about datums. So a datum is a reference surface for measuring locations on the Earth. A datum has two major components. The specification of an ellipsoid, which is an ellipsoid that has been surveyed and defines the origin and orientation of latitudes and longitude lines. We cannot assign any coordinates to a location without first specifying a datum and linking that datum to the shape of the Earth through field measurements. Horizontal datums give us the capability to measure distances and directions across the surface of the Earth. Most horizontal datums define a zero line at the equator from which we measure north and south latitudes. There is also a zero line at Greenwich meridian from which we measure east and west longitudes. Together, these lines provide a reference for latitude and longitude expressed in decimal degrees. These latitudes and longitude positions, or geographic coordinate systems, are based on a spheroid or ellipsoid surface that approximates the surface of the Earth, also known as a datum. All coordinates are referenced to a datum. A datum describes the shape of the Earth in a mathematical term. A datum defines the radius, the inverse flattening, the semi-major axis, the minor axis, and for your ellipsoids. Oh, wrong way. There we go. So, in its simplest definition, a vertical datum is a reference that we use for measuring heights. A vertical datum is found by measuring gravity and identifying variations in constant gravity, or equipotential surfaces, and then combining these with carefully measured control heights above a specific equipotential surface. So, our two most common vertical datums for North America are the National Geodetic Vertical Datum of 1929 and the National American Vertical Datum of 1988. In 2022, we're hoping that the NGS will release a new vertical datum, which will be a wonderful hybrid model of geoidal and sea level heights. So, a datum adjustment usually results in a change in coordinates for all existing datum points, as coordinate locations are estimated for both old and new datum points. The datum points do not move, but our best estimates of the datum point coordinates will change. Differences between the datums reflect differences in the control points, survey methods, mathematical models, and assumptions used in the datum alignment. The datum points never move, remember that, but the best estimate of their locations does change over time, relative to the origin set by a new, more complete set of data points. So here's an example of a benchmark. For those of you that like to do hiking or work in the survey field, you've probably seen these all around. They're often placed within very stable surfaces such as concrete or strong rock, and they represent a high precision measured point on the surface of the Earth that'll be used by NGS or the National Geodetic Survey to try to help maintain and improve our geoids and our ellipsoid models. So there are three common datums that you will use at GIS. The first datum we will discuss is the North American datum of 1927, also referred to as NAD27. The NAD27 datum is based on the Clark 1866 ellipsoid, which holds a fixed latitude and longitude in Kansas. The locations were adjusted based on about 26,000 measurements across North America. Quite a bit of GIS data is still available in NAD27. However, more recent data should use the North American datum of 1983. The North American datum 1983, or NAD83, is the successor of NAD27 and uses an Earth-centered reference ellipsoid rather than a fixed station in Kansas. Additionally, 250,000 points were measured to adjust the latitude and longitude locations. It's worth mentioning that it's okay to use NAD27 or NAD83. However, when performing analysis, you should convert all the data into a single datum for analysis purposes. The third common datum is the World Geodetic System in 1984, commonly referred to as WGS-84. WGS-84 is based on satellite measurements, and the WGS-84 ellipsoid, which is similar to another ellipsoid named GRS-80. The major difference between WGS-84 ellipsoid and the NAD27 and NAD83 datum is that the WGS-84 data has worldwide coverage, where NAD27 and 83 should only be used in North America. You should also note that WGS-84 datum is used by the GPS system to report latitudes and longitudes. Datums are not static, and we often see updates and adjustments throughout time. In fact, both NAD83 and WGS84 have been updated multiple times. Therefore, it's very important to read the documentation of the datasets that you're using in your GIS to determine exactly which datum was used to determine locations. So, converting geographic coordinates from one datum to another typically requires a data transformation. Datum transformations provide the latitude and longitude of a point in one datum when we know them in another datum, So our datum shift, which is different coordinates for benchmark datum points based on new datums. So the points have not physically shifted, like we said before, but the estimates of the coordinates have changed based on new measurements or better systems. The data transformations, which provides position of a point in one datum from another datum. The amount of shift between datums varies across the globe. If you're wondering why, it typically is because we're using different ellipsoids. So, some data transformation factors to keep in mind. When changing changing datum changes best estimates of our coordinates, not the physical locations. One should assume that coordinate shifts are significant unless you can prove otherwise. Datum transformations are estimated and are developed with a specific data set and for a specific area and time, meaning that how long it's been since it was done has an effect on what it's going to be like today. And that GIS projects should not mix datums if at all possible. Datum transformations are not always well documented in GIS software, so do be careful. Alright, so now let's talk about coordinates. So, once a size and shape of the reference ellipsoid has been determined, the poles and equator are also defined. The poles are defined by the axis of revolution of the ellipsoid, and the equator is defined as the circle midway between the two poles at a right angle to the polar axis, and spanning the widest dimension of the ellipsoid. We now must go about defining a coordinate grid, a reference system by which we may specify the position of features on the ellipsoidal surface. So, you can give anything on Earth latitude and longitude coordinates. This is why space is important. We represent it with coordinates or maps. So, how do we represent this space numerically? Well, obviously, we're going to use coordinates. And what accuracy do we need? Well, that's going to depend on our study. If we're looking at a map of the entire United States, if we're 50 meters off, you're not even going to be able to tell. But if we're looking at a map of Corpus Christi, Texas, or better yet, a neighborhood in Corpus Christi, Texas, you're going to notice if you're 50 meters off. Hell, you'll even notice if you're 1 meter off. And then we're also going to take a look at two-dimensional and three-dimensional coordinates. So, to quickly get away from coordinates, we're going to talk about accuracy and precision. So, to surveyors, accuracy refers to how closely a measurement or observation comes to measuring a true value, since measurements and observations are always subject to error. Precision refers to how closely repeated measurements or observations come to duplicating measured or observed values. Alright, so let's start off by talking about 3D coordinate systems. As it pertains to Earth, we use three-dimensional coordinate systems which represent a sphere, such as the Earth. The important thing to note about the 3D coordinate systems that we are going to discuss in this lecture is that we will not ignore the curvature of the Earth, which makes it ideal for displaying locations and measuring distances across long distances, where the curvature of the Earth will become a factor. The 3D coordinate system that we're going to discuss is going to use two angles of rotation, commonly known as latitude and longitude, and a radius to specify the location. The angles of rotation will determine whether the location is north or south of the equator, or east or west of the prime meridian, and the radius will specify how far from the center of the Earth that location is. Longitude, also known as a meridian, is the angle of rotation measured east and west around the globe. What may be confusing is that the lines of longitude run north-south from the North Pole to the South Pole. Lines of longitude will vary from positive 180 degrees east to negative 180 degrees west, measured relative to the line of longitude of 0 degrees, which is known as the prime meridian. The prime meridian runs through Greenwich, England. Lines of longitude west of Greenwich, England go up to and including 180 degrees are represented as a negative number and or as a western longitude. Lines of longitude east of Greenwich, England, up to and including 180 degrees are represented as a positive number or as longitudes. The second angle of rotation is known as latitude and is also referenced to as parallels. Parallels measure north to south on the globe, and the lines run in parallel to each other from east to west, from the North Pole to the South Pole. The equator is the latitude of 0 degrees. Lines of latitude measure from positive 90 degrees north, which is located at the North Pole, to negative 90 degrees south, which is located at the South Pole. Geographic coordinates do not form Cartesian systems. Cartesian systems define lines of equal value to form a right-angle grid. Geographic coordinates are defined on a curved surface, and the longitudinal lines converge at the poles. Therefore, there are no Cartesian parallels in the north-south direction, and the Earth's surface length of a degree of longitude varies from approximately 111.3 kilometers at the equator to 0 kilometers at the poles. So, spherical coordinates are most often recorded in a degrees, minutes, seconds notation. Minutes and seconds range from 0 to 60. Alternatively, spherical coordinates may be expressed as decimal degrees. Examples for conversion from DMS to DD and back are shown in Figure 2.7 of your textbook. Horizontal datums. So, we have defined a geographic coordinate system that provides for specifying locations on Earth. This gives us the exact longitude, This gives us the exact longitude of only one location, the Greenwich Observatory. By definition, the longitude of the Greenwich meridian is 0 degrees. We must estimate the longitudes and latitudes of all other locations through measurements. We establish a set of points for which the horizontal and vertical positions have been accurately determined. All other coordinate locations we use are measured with reference to this set of precisely surveyed points, including the coordinates we enter in our GIS to represent spatial features. Many countries have a government body charged with making precise geodetic surveys. For example, nearly all horizontal locations in the United States are traceable or related to a national network of highly accurate survey points established and maintained by the National Geodetic Survey. This unit of the U.S. federal government establishes geodetic latitudes and longitudes of known monumented points. These points, taken together, form the basis of a geodetic datum, upon which most subsequent surveys and positional measurements are based. So, you'll sometimes find degrees given in decimal degrees instead of more common degrees, minutes, and seconds. However, it's not easy to convert from a decimal to a sexagesimal system. For example, you need to combine data from maps that are calculated in two different systems. GPS systems, for example, when geocaching, should be able to switch from the different coordinate systems. Seen in the slides here are a few steps on how to convert from decimal degrees to degrees, minutes, seconds, and vice versa. You can also find a plethora of great tutorials for this on YouTube, as well as online calculators to do the math for you. But it's still important to be able to know how to do this on your own. Alright, so now let's talk about two-dimensional coordinate systems. Spatial data in a GIS most often uses a Cartesian coordinate system. So, named after René Descartes, a French mathematician. Cartesian systems define two or three orthogonal axes. Two-dimensional Cartesian systems define x and y axes in a plane, like the figures here. Three-dimensional Cartesian systems define a z-axis, orthogonal to both the x and y axes. An origin is defined with 0 values at the intersection of the orthogonal axes, like the figure on the right. Cartesian coordinates are usually specified as decimal numbers, by convention increasing from the bottom to the top and from left to right. Started at the bottom, now we here. Sorry, I like that song. Not really, it's just catchy. All right, so it's important to point out that with Cartesian coordinates that the GIS data, or excuse me, that Cartesian coordinates are typically used for GIS data. You also need to know that Cartesian systems ignore the curvature of the Earth. But for small areas, this is usually acceptable. So the two-dimensional Cartesian coordinate can represent many possible locations at many possible scales. It's so flexible, you can even create your own. However, there are two common representations that are widely used in North America and the world. The first being the state plane coordinate system, and the second being the Universal Transverse Mercator Coordinate System, or UTM. The state plane coordinate system is a set of 126 geographic zones that cover the United States of America. Each zone is designed specially for that region of the United States of America that it's covering, and is useful because it allows for simple calculations and is reasonably accurate within each zone. In the state plane coordinate system, coordinates are always positive inside each zone. The state plane coordinate system can be used off of NAD27 and NAD83 datums, and the coordinates are represented and measured in feet. Each state may have multiple state plane zones, but this is not required. Each zone is strategically placed to minimize the amount of error within each zone. Additionally, each zone provides a common coordinate reference for horizontal coordinates over areas such as counties, while limiting error to specified maxims. Depending on the shape of the state plane zone can be based on two types of map projections: the Lambert conformal conic or the transverse Mercator. This is an illustration of the state plane zones of the contiguous lower 48 United States of America. Notice that most states have multiple zones, and that zones typically either run north to south or east to west. Also note that most of the smaller states, particularly the New England area, only have one state plane zone covering the entire state, while larger states such as California and Texas have multiple zones, so their error could be minimized throughout the state. A notable exception to this is Montana. It's a large state, but it only has a single zone. State plate zones are typically designed with the name of the state, followed by a section indicator such as north, central, or south, or a combination of those, or west, central, east. A notable exception is California, which specifies each zone using a different number. The state plane coordinate system was designed for large-scale mapping in the United States. It was developed in the 1930s by the U.S. Coast and Geodetic Survey to provide a common reference system to surveyors and mappers. The goal was to design a conformal mapping system for the country with a maximum scale distortion of 1 part in 10,000. Then consider the limit of surveying accuracy. A different set of parallels is defined for each state plane zone. These parallels are placed at 1/6 of the zone width from the north and south limits of the zone, as seen in the figure here. The zone projection is defined by specifying the standard parallels and a central meridian that has a longitude near the center of the zone. The central meridian point in the direction of the geographic north, however, all other meridians converge to this central meridian, so they do not point to geographic north. The Lambert conformal conic is used to specify projections for state plane zones for 31 different states. Another standard coordinate system has been based on the transverse Mercator projection, distinct from the state plane system. This system is known as the Universal Transverse Mercator Coordinate System. The state plane system is defined only for the United States, but the UTM is a global coordinate system. It's widely used in the USA and other parts of North America, and is also used in many other countries worldwide. The UTM system divides the Earth into zones that are 6 degrees in longitude wide, and extend from 80 degrees south latitude to 84 degrees north latitude. The UTM zones are numbered from 1 to 60 in an easterly direction, starting at longitude 180 degrees west. Zones are further split north and south of the equator. Therefore, the zones containing most of England is identified as UTM Zone 30 North, while the zones containing most of New Zealand are designated as UTM Zones 59 South and 60 South. Directional designations are here abbreviated, i.e. 30 North, 30 in place of 30 North. The Universal Transverse Mercator Coordinate System is a worldwide two-dimensional coordinate system that splits the world into 60 zones. The Universal Transverse Mercator Coordinate System is useful because it provides for simple calculations and it manages error within each zone. Unlike the State Plane Coordinate System, which is measured in feet, and the Universal Transverse Mercator Coordinate System, which is specified and measured in meters. So, the UTM coordinate system commonly is a global coordinate system where each zone is 6 degrees wide at the equator and extends from 80 degrees south to 85 degrees north. Each zone is numbered 1 to 60, heading east from 180 degrees west. That is, on the opposite side of the Earth from the prime meridian. Those are also split in north and south about the equator. So, Zone 3, for instance, will have both a Zone 3 North and a Zone 3 South designation. UTM is common for data and study areas that cover large regions or regions outside of the United States. It's important to note that coordinates are always positive and specified in eastings, which is the vertical axis, and northings, which is the horizontal axis. So the UTM system specifies a unique transverse Mercator projection for each UTM zone. Each projection is centered on the zone's central meridian and extends east and west to cover the 6-degree wide region. The figure shown here, as in the figure shown here. Distances in the UTM system are specified in meters north and east of the zone origin. The y values increase in a northerly direction, and the x values increase in an easterly direction. The origins of the UTM coordinate system are defined differently depending on whether the zone is north or south of the equator. In either case, the UTM coordinate system is defined so that all coordinates are positive within the zone. So, the UTM coordinate system is common for data and study areas spanning large regions. In other words, several state plane zones. Many data from the U.S. federal government sources are in a UTM coordinate system because many agencies manage land spanning large areas, and the UTM is a well-known standard system. Because the UTM zones are 6 degrees wide, there are many large area projects that would not fit in one state plane zone but do fit into one UTM zone. Utah, Indiana, Alabama, and other states fit entirely into a single UTM zone, while many other states are predominantly in one UTM zone. For example, most of Colorado is included in a single UTM zone, 13. All right, so that concludes today's specific lecture on coordinate systems, geodesy, and projections. We will get into more detail on some of these in future lectures. Thank you for having me. As always, if you have questions, feel free to ask me in class, send me an email, or post questions here on YouTube. If I see them on YouTube, I will be sure to answer them as soon as possible. All right, thank you. Have a good one.